Okay, so
This is on.
Yeah, just turn you off, okay? For the Q.
Il y a 2 ans à Nantes, ils avaient fait, et tout était marqué, c'était très clair.
Ah, et là, c'était pas marqué? Ouais, c'était le même ordre.
Ils ont mis les frais d'inscription après qu'ils ont dit.
Okay, so we will start the session. So I want to welcome you to this EPSC 2014 edition of the AEAM1 session, which is focusing on amateur contribution to planetary science and exoplanet science. This session was prepared by myself, Christophe Pellier, Alexandre Santerne, Olivier Moussy, Padmaya Namandra Fischer, Tony Cook, and Mr. Montalto. So, basically for the program, we will have a change at the end. We will talk rapidly about the posters because we have one cancellation for the oral. But for the rest, we will follow the program. So I'm really glad to ask Glenn to start talking about Juno mission. Okay, so.
Hoping for the best.
Okay.
Okay, running on a new system. So, good afternoon, all astronomers. I'm glad to be back here again after a couple of years. What I want to do is talk to you my basis of both as an observational astronomer using somewhat larger telescopes than my 8-inch Celestron, which is unfortunately probably gathering dust in the back of the house, with 8-meter telescopes, and now with the Juno mission, which is on its way to Jupiter. What I want to do is talk about the Juno mission, summary of what we're doing, its status currently, and the orbit plans, the supporting role of Earth-based observations for different aspects, and our priorities. What I'm going to recommend are logistics and techniques and the format of data that we'd like to see. Juno science will improve our understanding of the history of the solar system by investigating the origin and evolution of the planet. To accomplish this, we're going to investigate Jupiter's origin, interior, atmosphere, and magnetosphere. What we learn from Juno will also vastly improve our general knowledge of how giant planets in general form and evolve. They shape the evolution of planetary systems in this and other solar systems. We're going to probe the deep interior for orbit in 3 different ways. We're going to map the deepest interior to the atmosphere using microwaves, magnetic fields, and the gravity fields. 3 different experiment types, which will define different parts of the mission. We're going to define microwave radiometry measured by the microwave radiometer, and you'll see this acronym MWR throughout this. That's measuring microwaves at thermal radiation to as deep as 1,000 atmospheres of pressure. That's 1,000 bars, 500 to 600 kilometers below the visible cloud tops, determining water, ammonia abundances in the atmosphere, and how they're distributed across the planet. We cannot do this from the Earth because at these wavelengths, we get synchrotron radiation, relativistic electrons emitting, so we can't see what's happening on the planet. A second approach, and a different part of the mission, is to map Jupiter's gravity by looking at precise Doppler measurements of the spacecraft motion as it passes very close to the planet. We're going to be in orbits that are just 4,000 kilometers above this cloud tops of a 70,000 kilometer radius planet. Very, very close, and beneath the radiation fields for the most part. We're going to be getting further clues from measurements of tides in the atmosphere. And the third approach, which I'm not outlining here on visually, is measurements of the magnetic field, which are going to be tied to the structure of the interior. So Juno, if I can get this to work, is currently on its way. We have successfully passed Earth orbit don't know if there's a way of getting these lights off. That may be helpful. We're on our way out now and heading toward an initial encounter with Jupiter on Bastille Day in 2016, July 14. And here, when we approach Jupiter, we're going to go through some orbital corrections, a large sloping orbit, then a correcting orbit, then one that will be tweaking ourselves in October of 2016. And it's around here that we expect to get the spacecraft into a position that will ultimately be looking somewhat like this. You can see the planet. We are on the terminator, and we're rotating. This is a spacecraft that is not three-axis stabilized. It's rotating all the time, and it's known now for these very large veins of electric cells which are pointed at the sun. This is a non-nuclear spacecraft, the first thing to be of this type at Jupiter, 5.2 AU from the sun. Thank you. That's good. Now, of course, I've got to see what I'm doing. So when the orbits we get into then are going to be very long elliptical looping orbits like this. So pretty much every 11 days we have orbits that are very strung out. The first few of which are going to be remote sensing. They're going to be identified in a later slide as MWR orbits. Eventually at orbit, the rest are gravity sensing, and these are going to be coming in at like orbit 34. We then plunge into the planet so we don't deliver Earth microbes to Europa or some other abode of life. The spacecraft itself is going to have a number of sensors. The microwave radiometer and gravity science magnetometers are a part of the sensors. You can see magnetometers on the end here. Jade and waves are also sensing electric fields, plasma waves, and particles. We're going to be concentrating on the microwave radiometer and the ultraviolet spectrometer, and GRAM, which is a 2 to 5 micron imager and spectrometer, and JUNO-CAM, which will be our visible camera. A little bit close-up of this close-up. So microwave radiometer, I'm going to see is MWR, UV spectrometer is UVS, the infrared camera is GRAM, Juno infrared auroral mapper, and the visible camera JUNO-CAM. They're located on these parts of the spacecraft, and the MWR has several panels like this, again, as a spacecraft is rotating constantly. So why do we need in remote sensing support? First, we want to have help in predicting where features are going to be. We have a little bit of play about what we see, not a whole lot. No, not end show. So we see here's a graphic of these orbits in a different way in the plane. What this is not showing correctly is the fact that all of these are going to be at the terminator of the planet, and of course Jupiter is going to be rotating much faster than these things are going to go by. But these orbits are going to intersect the planet from a long distance and close in very much. Once these are done, at the end of a 5-year cruise, we're going to need to know 3 to 6 months ahead of an arrival time, timing of this initial perijove. So whatever features we see must be based on predictions and data before the 2016 January to April time frame, which is the 2015-2016 apparition. We can change the initial orbit by plus or minus 20 minutes. That's all. That'll give us a play of about plus or minus 12 degrees of longitude. If we need it, we can tweak the orbit so that we have a better chance of seeing one of the priorities is the Great Red Spot, and which is going to be fairly easy to predict where it's going to be, and then 5-micron hotspots, which are not so easy. And why do we want those? 5-micron hotspots are big open areas in the atmosphere of Jupiter that are very desiccated, very dry, and pretty cloudless, but it's where the Galileo probe went into one of these. We'd like to connect what we're seeing in Juno mission with what we saw in Galileo. If we can target one of these and establish what the conditions that we're seeing here, we can make that connection more or less directly, or more directly than if we're just using theory. One way of doing this we did in Galileo is to line up, get a zonal mean speed, and these are excerpts from cylindrical maps of Jupiter right at the 5-micron region that will more or less tell us, and the better we get, the better closer we are to where these things are going to appear and where we might tweak the orbit one way to improve our chances. There's no guarantee, as we discovered on Galileo. So why am I asking amateur astronomers to observe 5-micron hotspots? Well, there's a correlation. If we look here, 5-micron emission from cloud tops, it's not coded red the way I like to it, but if you look at this panel, you note that there's a big correlation between these and observations of dark blue-gray regions that are just south of the north equatorial belt, right in here. You can see this a little bit better if you look at a Hubble image, 763, which was simultaneous with a 5-micron region. So we can actually tell where these are from the visible range. In fact, just a red filter. If we go to an ultraviolet, we can't tell very much, but actually we can tell where the great red spot is going to be, and the oval BA. So we also need contextual observations over the globe. JunoCam, for example, is not a scientific grade camera with calibration. It lets me taking images, and you can vote on where it's going to be pointing. It's an education public outreach camera. It just has, I'll describe the filters it's got, but this is sort of good for the public, including all astronomers, including amateurs. The data will be available for everybody right away. But for us on the science team, we'd rather have lots of images along the track of the spacecraft, so we may not be able to see what it is all the other instruments are looking at. So we need some other way of doing that, and that's where everyone in the whole world will come in. So what I'm showing now is a simulation of what we see in one. Here's one orbit, the periapsis, and here's where we download a lot of the data we took during that periapsis. And we're on our way back, that's an apoapsis, and we come in and we get to this, you get the sense of the roller coaster sense of this very highly elliptical orbit. Here we go, we get great images of the pole, but when you get close to the planet, we don't see very much. We have, in fact, here's a microwave spectrometer, radiometer track. You're going to see these tiny little footprints. We're rotating in this direction. We're not going to get anything in the other direction. So we need to figure out what it is that we were looking at, this rotation. At this point, we're heading, the high-grain antenna is off Earth, and when you get down to the apoapsis is when we download the data set. So for JunoCam, for example, we have for one microwave radiometer orientation, which is pointed down toward the nadir that is directly below the spacecraft. These are the fields of view we get if we're pointed the way most of us on the mission would like the camera to point. They could be off as well. For the whole mission, for the orbits that are designed for the microwave radiometer, this is all we'll get for the entire planet. So we want to know whether what we're seeing are part of a wave structure, or they represent global mean properties, or are there perturbations, zonal or meridional motions or winds? We don't know. We're going to have to depend on contextual observations. Also, we want to know what has been the evolution of the features in time. For example, one of the big features that we see and has a great deal of change in is the Great Red Spot. If you looked at this in the late 19th century, you'd swear it's the Great Red Sausage. It's so long. We're seeing this evolution down to a smaller extent from the Voyager image, and more recently from Hubble, we see from 95, 2009 to 2014, a great diminution of the longitudinal extent of the Great Red Spot. We want to know what's going on then and what will take place ahead. By the time we get there, it may be the GRC, the Great Red Circle, and I hope it's not the GRM, the Great Red Memory. So, what are the observations that are useful? We have great images of the whole disk in RGB filters, and maybe whatever filters are possible that you can get, like the 890 methane band, other narrow filters. Again, we want these before to predict the locations at the same time as the MWR orbit parajoes for global context, and in between. Detect short-term changes of atmospheric features and maybe create movies, the way the Swedish group did for the Voyager 3 movie. Here are the orbits we're going to get. You notice everything in green is a gravity sensing orbit, and our remote sensing orbits, the dedicated ones, are located here in the beginning. Partly that's to avoid degradation of the camera with the constant radiation field. But notice that there aren't that many ground-based observations that can, Earth-based observations that can get this. Hubble can only start doing this with a 50 degree west avoidance angle from the sun. Even the IRTF can't get this first orbit at all. So we'll have to see. The 8-meter telescopes don't want to sit in the sunlight at all. So at this point, we get only 30 minutes on the planet. We have to get the rest of these. And in fact, even more than what we're getting the difficult difference between these is that For the remote sensing MWR orbits, we're pointing straight down. For gravity sensing, we're pointing to the Earth. We're still going to be able to get some things. And in fact, for the gravity sensing, we're going to be tilting for the Juno cam actually further away from the darkened region of the planet in the Terminator than we would otherwise. So this is not a problem for us. So in addition to these, we want maybe after the MWR orbits to support targeted opportunity observations, we get in gravity sensing, and after to follow up the evolution of features. So what we can see, an example of what we want to do using red, green, blue filters. We will take anything you give us, but we recommend it's sort of the video approach that uses Regisax or AutoStacker, which selects and aligns the best features that make very good images that look like this. If you get the further stability, you can use WinJOPUS and project different colors onto a latitude and longitude grid, combine them and reproject onto a spheroid, and then project back, and you can get some extraordinary images. This one is a particularly good astronomer, Anthony Wesley, bird. What I really want to see, though, and now this is sort of the bottom line, we don't want you to stretch the images or change the linearity. So turn off the histogram stretching before you register and stack. Save in FITS, PNG, or TIFF. Anything you do in JPEG or GIF is going to destroy the linearity, because we have what the 0 is. Ask for the highest depth option. Send an IMS text file or something that tells us who made the image, where, what time, and which filter. If you want to send a sharpened image, but also send us something that hasn't been subject to a wavelet on-chart masking procedure, we can do that ourselves. Thank you. You can also do a cylindrical map flattened by a Lambertian law, and that's an option within WinJOPUS, and compress the result. Now, these two steps can also be, we're working with Grisha Han and the JUPOS group to make some of these automatic options within WinJOPUS, and you want to be able to tie testing that with a Jupyter apparition, and you can currently just archive these with PVOL, but right now we're exploring a Juno or Juno affiliated site which might display the images automatically when they're deposited and allow us on the team to get immediate access. So if you have any questions, here's my best representatives here, Anthony Wesley, and the JUPOS team. Give me a shout out at glennorton.jpl.nasa.gov. Thank you.
Okay, thank you, Glenn.
Yeah. Questions?
Thank you. I was just wondering, is there a site that all that information is on so that we can access it?
Talk to me, not yet.
Okay.
There's a Juno meeting in 2 weeks. I can't have too many meetings in 1 month. And we're going to try to pull up that information and try to figure out whether we can pull up the website for that. So it's part of this is I'm deferring a little bit because that's TBD, and I'd like to get that set up.
Okay.
All right, but talk to me and I'll try to get that slide at least, or Mark has downloaded the text so you can talk to him too.
Thank you.
Okay.
I have a question about Juno itself. Are you able to probe the region of metallic hydrogen to give us more information about what it is? Because it's very hard to make it.
Yohai can answer that. Maybe with gravity.
So you'll be able to understand it in a bit more better context. Because at the moment it's very hard to understand what it actually is. We can't read it.
Gravity will help us understand and also understand how deep the dynamics is.
Okay, thank you, Glenn. It's time now to switch from amateur support to the Juno program to amateur support to COMETS program. So Padma Yanamandra Fisher will talk about that when the techniques are here.
Thank you all for coming. This is an interesting outreach and a science project where we are basically having a project called the PACA project, stands for Pro-AM collaborative astronomy, and right now it focuses mostly on supporting comet observations for various types of campaigns. One is a mission support for ESA Rosetta mission. The other campaign is driven by NASA wanting to coordinate all the observations of Siding Spring. And both of these are based on a successful campaign we had earlier last year for Comet ISON. Okay, why do we want to study comets? Anybody interested in learning how our solar system formed is pretty much eventually at some point going to study comets because they are the remnants of the formation of the solar system. So they contain information and also possibly materials that were extant at the early formation of the solar system. As you can see, this is a family portrait of the solar system taken by images from Voyager. And what you see is there's a variety of planets, and they all have different types of atmospheres. Some don't have atmospheres, or they have moons. And so all of this diversity, if it's formed, some of these clues to that are probably locked in the comets. And so what we want to know is where did they come from, how are they formed, and how did they evolve, and what can we learn about the conditions under which these planets formed. So one of the best things to learn or study is the spectral energy distribution. That is, from all across the wavelength electromagnetic spectrum, you learn something about the comet by looking at it at different wavelengths. And so, since comets, most of them that are discovered from ground by amateur astronomers, we don't have enough time to either plan a coordinated campaign nor a mission, and therefore what we need to do is we need to bridge observations across the multiple spectral windows, and we also need to bridge the pro and amateur communities so that we can have the feedback and the legacy and the long timeline of data that we get from the amateur data. And so this is just a cartoon of showing how there are several reservoirs where comets come from, and then there are different types of properties at different wavelengths that are important to learn the composition, the optical properties of the particles in the comets, as well as their temperature and thermal emission. And each one of these intervals gives certain observables that we put into models. And right now, I'm only going to be talking about the optical because that's what the amateurs can do, maybe some near IR, but this is where we are going to focus our talk on. So here are some recent contributions. Have you done this before with amateurs? Yes. The first one being Comet Halley. There was one of the first coordinated amateur global campaign, and one of the science results that came out was based on all these collections of amateur astronomers' data, that there are these disconnection events that occur in the tail, and that happens whenever the comet goes across a boundary, a sector boundary of the underlying helios sheath, which is related to the solar wind. And so that really gives you it's like a marker. It's like a marker telling you how the local solar wind field changes. And then, of course, in 1994, the famous SL9 comet, it disintegrated into fragments, and then they all crashed into Jupiter, one by one. And so over a course of a week, we see all this impact happening. And 15 years later, we still see remnants or traces of water that was deposited into the planet's atmosphere by SL9. This is a Herschel image. And then last year, there weren't any missions, but Comet ISON was very exciting because when it first was discovered, it was thought to be a return of one of the great comets of 1882. However, as the orbit got refined better, it turned out to be it wasn't that, but it had a promise of being a great comet. And here is just a cartoon of its evolution, the start of its disintegration, and then when the disintegration occurred, all the dust out of the nucleus is coming out in the tail, and then after that, it disintegrated on Thanksgiving Day in the US, that is November 28, corresponding to its perihelion. And of course, we had a huge global network of amateurs, and these are the images, some of the best images that were taken, were selected as the winning entries in a global photo contest. Out of the 6, 4 of them were members of our amateur group. So now, in addition to the evolution of a comet, there are certain geometrical effects that occur which you cannot predict. It depends on the orientation of the Earth going through the orbital orbital plane of the comet. And so some of them you can actually see have things like what are called anti-tails. This is a sharp structure that occurs in front of the comet. And this was the first one that was of any note, like R.N. Rowland in '57. But last year, one of our imagers, our amateur astronomers, Roland Ligustri, looked at Pan stars and saw this beautiful anti-tail that lasted for almost a week to 2 weeks. And we also saw, excuse me, and we also saw, like Halley, there were several comets, Lemon as well as Lovejoy and ISON, that showed disconnection events. And so we are partnering with the investigators at the University of Central London who are actually studying how these tails can tell you what the solar field looks like. And then, of course, there are fragments and outbursts that happen. This is a famous Schwarzmann-Wachmann 3, and it's one of the famous fragments. This is a Spitzer near-infrared observation. This is SL9. And so all of these things can happen, and you can't predict this. That's why what we need to do is we need to have a continuous monitoring program which is supported by the amateur astronomers. And so here's the success of ISON. And this logo was actually this logo was created for the campaign by one of our amateur astronomers. It's stuck.
It works.
Anyway, I'll continue talking. So the highlight of Comet ISON campaign was that in this era, everybody uses the internet, but also they use social media, Facebook, all the other attributes of social media, that we took advantage of. We took advantage of that by creating a Facebook group, Twitter, Pinterest board, all these other dimensions, so that we could reach not only the amateurs very quickly, but the amateurs could post their images quickly for us. And they posted the images, but the data is the FITS data, the scientifically valuable data is separate from it. And also we were able to do some first round of science. That is, here's one, what's called AFRO. AFRO is basically a quantity that is that is defined to be a proxy of the dust activity. And so what it shows is as it changes, you can identify outbursts. This is the beginning of discovery of ISON. And then it became quiet, and when people thought it wasn't going to be as bright as we thought it was going to be, and there's no activity, and so this is very flat. And then towards the end, before disintegration, it had this sharp spike showing that the dust production is kind of stopped and the gas production is increased, and this is the start of the disintegration. So in lieu of time, I'm just going to go ahead and run through quickly. And here's one interesting science piece that came out. We had an amateur astronomer in Spain, Granada, Spain, Tony Angel, that he essentially said, oh, the image looks like it has two beacons instead of two bright tails. And 3 hours later, once he told me that on Facebook, and we were chatting on that, I was at the RRTF, NASA RRTF in Hawaii, looking in mid-infrared at the emission of the comet. And so this was the day before he saw this, and right after, a few hours after seeing this kind of a feature, we see that they're actually taking the temperature of the outburst. And it's the only one spectrum that we get, and we did it because we were always in contact with our amateur group. And so now we have a first paper out which uses the AFRO measured from the amateurs' data. This is our data from Calar Alto and Sierra Nevada. And then this is data taken from the solar spacecraft SOHO and STEREO. And so putting all this together, we are able to model the dust before and after perihelion. So based on that, this is where we now have this project called PACA, and essentially we have pretty much a core group of amateur astronomers that belong to it, and we have integration of all the social media. We take observations in different ways. That is multispectral, some take spectra, many of them are doing just regular images, and we're trying to do polarization also. All these things taken together tell us something about the comet dust particles. And also we're trying to have a consistent standard for how to report the data. We prefer FITS format. However, we want to make sure that there are several ways that the amateurs can not only take the data, but also to be able to share it with us. And also we have different websites where we produce different products that we can display. And then of course, like here, I have several of my amateur astronomers here who are also sharing their results. So this is, we're propagating the fact that amateurs have an equal role, and as partners, we can actually do a lot of science. And so here, Siding Spring is very interesting because the Siding Spring is going to be going by Mars on October 19th. It's very similar to ISON, as ISON looked at this distance from the sun. And it's essentially getting two campaigns for the price of one. You're getting a comet and a planet. And so because of the lead time for Mars, we are going to be studying the influence of comet dust. Luckily, it's not going to be too close, and it's not going to impact the planet, so you're not going to have a lot of risk to any other spacecraft. But it's over the period of time that we're observing it, the seasons are changing. So we saw it go from spring to summer, and now it's started its fall season, which is the dust storm season, a month before the close flyby. And so therefore, if there's any dust that settles in the atmosphere of Mars, then we may see presence of cloud systems like noctilucent cloud systems on Earth. And so therefore, the Siding Spring Comet campaign is going to be mostly in the southern hemisphere, so this is where we're focusing. And I won't read everything here, but the point being that ultimately we are working in NASA headquarters trying to create products for the amateur astronomers and the public, because that's one of the places where the comet is going to be circumpolar, so you can see it all through the night. And so here are some of the images that we have received from our amateurs. And here's Mars campaign, Wesley, Pellier, we have Kaufman. All of these are my amateur astronomers who have been monitoring Mars. And so they have full rotations of this. So you can actually see dust fronts moving across the planet over time. And this is a spectrum of the planet. So this is the level of activity we have going on. And so these are just... And so this is Encounter Day. As you can see, South Africa, this is where we are planning to have observers. But this information was provided by an amateur astronomer who was trying to plan his program. And therefore, this is Australia, but we see mostly here. And then we are trying to find observers here in Argentina and Brazil. But the neat thing about this is even though you can see it from southern hemisphere, the southern hemispheric sky is very, very busy. So both the planet and the comet are going to be crossing each other, but in a very dense part. So we're trying to develop strategies on how to be able to monitor both of them and to get some information from that. And then, of course, Rosetta, as the project scientist calls it, a very sexy mission. So even though I'm not going to go into detail. What I just wanted to quickly jump over into is this is the 7th time that the comet, Rosetta's Comet 67P Shirimo-Gerasimenko, or abbreviated CG, is going through the inner solar system, but every apparition is a little different. So this one is supposed to be a little fainter and harder, and it's more of a challenge. And so this is going to be interesting because Rosetta sends out very fantastic, high-resolution, in situ, very close images, but you still don't know what the global environment is. That's why you need the pro and am observers from ground. And so this is what we have. We have a ground-based campaign for professionals that's on this website, and the one for amateurs, which is what I'm running. It's basically a PACA group, and it has all the social dimensions, also a Facebook group. And so this, I'm going to kind of stop after this one, but why do you want to be able to observe 67P when a mission is already doing it? Well, this is what the mission is telling us now, that there's such a huge variety, a variability of the surface as well as the structures, things like sharp cliffs like this. However, here's an image from VLT taken just a few days before, showing that there is a coma already, so you can't see any of this stuff. It's not resolved. But you cannot see this extended coma from the lander or the orbiter. And then these are images taken a few months ago by an amateur astronomer using a telescopic, robotic telescope network. It's a half-meter telescope in Australia. And so you can see that they're able to detect it even as a magnitude of 20. So you need the different perspectives for different questions. So that's why this is going to be an interesting partnership as this mission progresses. And I'm going to kind of leave this slide as I finish because, like Glenn mentioned, The data, some of the challenges are the data formats are different from the amateur to the professional community, how to share it with software to use. And also one issue we have is where do you store all this data? So you want it both on the NASA side as well as the ESA side. So we're trying to work with both archival agencies, the Planetary Data System and the Planetary Science Archive, to see if they can dedicate some space on their servers for amateur data before it's ingested and into the system.
Okay, thank you very much, Padma. We have time for one quick question to catch up a bit with time. Sure.
Hi. So one of the things that amateur astronomers have access to that professional astronomers struggle to get time on is spectrographs. And comets can tell us a lot about the origin of water on the Earth. So is there any program to try and get spectra of comets to determine their D to H ratio to determine if we really did get them from comets or from other sources as well?
There are a few amateur astronomers that are spectroscopists, and so they're doing that. So we have to work with the professional spectroscopists really, because even though they may get very little data, or they'll have better resolution and they have better models. But we do, for ISON, actually it was one of the amateur astronomers that got the first spectrum, so you could tell it wasn't a very gassy nor a dusty comet compared to Lemon or Pan-STARRS. And so yes, there are people who are doing that, but it's not an easy target right now. It's very faint, and so you have to wait till next year towards close to perihelion, post-perihelion. That's when the comet really becomes bright.
Okay, thank you again, Padma. So now, next we will have a presentation from Jean-Eudes Arlot regarding what amateur can bring to the FEMU campaign.
Thank you. So I would like to present the observational campaigns of the Galilean satellite of Jupiter, which will take place in 2015. In fact, the observation, the astrometric observation of the Galilean satellite is very difficult because they are very bright. It's magnitude 5. And how to observe objects of magnitude 5? If you have them on your CCD image, you have no reference star because they are too bright. So they are the most brightest object near Jupiter, but they are very difficult to observe. In fact, they are very interesting because they are large height satellites, and we need observation to explain their formation, their evolution. So I told you about direct imaging. It's very difficult because you have stars, you have objects, and only the Galilean, nothing else. So during history, the observations were those of the eclipse by Jupiter. So you have here Jupiter, the shadow behind Jupiter, and when the satellite is going across the shadow, we have an eclipse. So we measure the timing of the eclipse, and from these observations, it's easy to make dynamical models, ephemerides. But the shadow of Jupiter is not very sharp because of the atmosphere of the planet. So the accuracy, the astrometric accuracy, is not very good. But it appears that the satellites themselves have shadows and mutual occultation. And that these events, photometric events, that we are asking for observations. And you see here you have the different kind of observation, astrometric observation of the Galilean satellites. And you see on CCD or photographic plates, I will say direct imaging, you have some discrepancies in the observations. And you have here the HST and the mutual phenomena. And you see you have same accuracy between those observations. And mutual phenomena, as I told you, it's easy. It's bright objects, so easy to observe. And during the next campaign, it will be very favorable for observations. Why? In fact, you have mutual events only when the Earth and the Sun are in the equatorial plane of Jupiter. Then you have some alignment, and from the Earth, near the Sun, of course, you have alignment between the satellites. And you see you have here the elevation of the Earth and the Sun above the equatorial plane of Jupiter. And you have the equinox on Jupiter on January next year. And around this date, you have mutual events between the satellites. And here I put the number of events for each month during this period. So you see you have many possible observations here. And we are lucky because we are around the opposition of Jupiter and the Sun. So, of course, when you have the conjunction, it's impossible to observe. You have Jupiter behind the Sun. But the maximum of events are near the opposition. And for the northern hemisphere, you have here the declination of Jupiter. It's very favorable for the northern hemisphere. So it's a very, very favorable occurrence for observations. What happened during mutual events? You have first the mutual occultation. Mutual occultation, you have one satellite going behind another one. So if you observe the flux, the photometric flux, you have a decrease, a magnitude drop during the event. Here you have an image with high accuracy. In fact, you don't need such image. I think it's some kind of lucky imaging to make this, but you don't need this because we need only the magnitude drop of the satellites. We don't need to see the satellites themselves. Here you have an eclipse, so you have the shadow of one satellite passing on the disk of another one. Same, here you have a magnitude drop of the flux received from the satellites. It's what we need for our goal. So what happens? You have here most of the time you observe something like that. 2 points becoming only 1 point with a magnitude drop, and then 2 points. It's a mutual occultation. In fact, you have this. You have the satellites going like this, and what happened? And you have here the light curve received from the satellites. So you need only the light curve. And from each point of the light curve, the flux is, in fact, a function of the relative position of the two satellites and other parameters depending on the albedo, surface, and things like that. So what we need, it's the light curve. That's all. This is an example of a light curve. And in fact, you may have an accuracy in the position of the satellites from 10 to 30 kilometers. That is better than direct imaging. We have maybe 150 kilometers. For example, the space probes provide a 5-kilometer accuracy. But to have such an accuracy, you need to date each point in universal time to the nearest 1/10 of a second of time. It's very important. And you need to make a good photometry. The photometry, you need a photometric camera when you are doing this, and you have to follow a very strict procedure. And you have to correct the background, of course. And you see here you have some background due to Jupiter, which is in this area. And when measuring the flux, you have to measure the flux of the satellites and the flux of the background around that. You have to subtract the background. And it's not the same background left, and right. So you have to make this type of measure. In fact, you need also, so that at the middle you have here a light curve during an occultation, but you need to record individual measurement of each satellite before and after the event. It is absolutely necessary in order to have a good photometric reduction of the observation. And another possibility is to put slightly out of focus the image. Why? Because when you have a bad seeing of the image, when the satellites are far each other, it's not a problem. But when they are close together, the two seeing are combined and the flux is increasing and you will have saturation of your camera. So to avoid the saturation, it's better to slightly put out of focus, except if you have a very good seeing, of course. And another recommendation is to use an infrared filter. You see at the 890 nanometers, you have the methane filter. And it's very interesting because Jupiter is very bright. And if you have a bright Jupiter too close of the satellite, the photometry is not good. So when you are observing an event too close of Jupiter, it's interesting to put an infrared filter like this. And if you have a telescope larger than 30 centimeters, it's possible to observe the eclipse of Amalthea by Jupiter or by another Galilean satellite. So we have a website for the campaign. You have here the address of the website with many information on the campaign and the list of the event, of course. And you have also ephemerides of the satellite, so at any time you may have this configuration. You have Jupiter and the satellites with position like this. And you have also the relative position of the satellites. You have also a page to send the observations being a succession of flux drop or image if you are not able to make the photometric reduction. And at the end of the campaign, as we did for the former campaign, we publish all the data in a catalog like this. So in conclusion, we will have a very rare event coming, and so we ask all amateurs to participate to this campaign and to join us for you have here the website, and you may send email to have information. Okay, thank you.
Thank you, Jean-Eudes. So, do you have any question for Jean-Eudes? Yeah.
Thank you, Jean-Eudes. We have observed, or had been observed, these mutual phenomena since 40, 50, 60 years, first with films and with videos. And
every 6 years, in fact.
Huh?
Equinox on Jupiter is every 6 years.
No, I mean, they have been observed different of these campaigns for even in the 19th century, they observed it. What is actually the scientific output at the end? I mean, you say the astrometry is corrected. Are there papers which describe this? So this is due to the mutual event determination. This is due to HST observations and so on. Is there some information about this? What is going on with these things? I mean, there's a nice catalog and so that we know. But where is the astrometric and influence of these observations into the general description of orbital movement of the satellites?
In fact, we need many astrometric observation of the Galilean satellites because they are very fast, 1 day and a half for I/O. And there are many difficulties in the dynamical model because of tidal effects of the mutual perturbation between the satellites, the gravity field of Jupiter, the influence of Saturn, of the Sun. So if we wish to have a model accurate during years and decades, we need a lot of astrometric observations. We have some observations from space probes. We have old observations, higher photographic plates, or observations of eclipse by Jupiter. And we need to continue to observe. At the present time, we have no space probe near Jupiter, and it's very difficult to get accurate CCD observations. So it's very important to have observation at that time, and in order to get enough observation for improving our dynamical model and understanding the evolution of the satellites and things like that.
Okay, so that means that the observations are really used for refining the dynamic models of the orbits.
It's very useful.
Thank you, Jean-Eudes. So it's my turn to present. Okay, so I will talk about the amateur contributions to planetary science, not only with their observations with their telescopes, but in that case, with using the professional 1 meter telescope at Pic du Midi. This work has been done with Christophe Pellier. Both of us are members of the Astronomical Society in France and the observatory, the Planetary Observation section. François Collat, Frédéric Vachier from EMCCE, and Jean-Luc Dauvergne and Jean Le Cacheux from S2P. Okay, so the context is that, of course, there are very nice professional observatories with very large diameter telescopes, but they don't observe planets that much. And when they do, they rather do it with, let's call it mid-infrared wavelength, basically above 1 micrometer. There are also, on the other side, some other professional telescopes with smaller diameters, which are a bit less used, and which work, due to their diameter, they work in shorter wavelength. There are also some amateur and advanced amateur whose experience is recognized by the professional community in terms of acquisition and planetary image processing. And as we have seen already in the previous presentation, professionals are asking for observation from amateurs. So this is the context. So talking about 1 meter telescope at Pic du Midi, the Bigorre in France, which is about 3,000 meters high. We have an observatory with a very good seeing, a very nice observatory with 2 professional telescopes, 1 2 meter and 1 meter telescope, plus many other ones. The 1 meter telescope I am talking about is a Cassegrain telescope with a focal length of 17.5 meters, which is 50 years old and which has really high quality optics. They were made by Jean Texereau, which was at that time extremely famous in optical mirrors. That telescope was used at the beginning for participating to the lunar cartography, for preparing the Apollo missions and identifying the landing sites. But of course, after the Apollo missions, it quickly moved on other topics, and these were researches on solar system bodies. So nowadays, it's used for several programs: giant planets monitoring, asteroid, NEOs, transneptunian objects, astrometries, and exceptional events like occultations or comet observation as well. So under François Collat initiative, the professional who is in charge of this telescope, there are a few advanced amateur astronomers who participate to this program by using this telescope. And I am one of the lucky ones. So this telescope, basically, from the beginning of 2000s, there was a big step forward with the use of fast digital cameras with lucky imaging techniques, which could really improve the quality of the images that we could get. And of course, such a large telescope with a 1 meter mirror is perfectly suited for small apparent diameter planets, mainly Mars, Uranus, Neptune. But at that time, for Jupiter or Saturn, the digital cameras which were used had the sensors which were too small to frame them, to have them within the sensor. So we need bigger, at least medium-sized sensors and in cameras for that. And starting in 2013, there is an additional use of a dedicated camera, the Neo Andor camera, which is a S-CMOS camera. And also, there is a slow scan CCD camera for longer exposure and for example, for asteroid observations. So, of course, for amateurs, it's quite a change. I mean, using such a telescope, it's not exactly the same size. Myself, when I go observing, I mount my telescope with a 30 centimeter diameter in my garden, and here this is a huge telescope inside a cupola. It's really quite a change with a computer room from where to use it. Of course, with higher resolution and sampling, and from our experience, of course, it's really incredible in most difficult wavelengths at planets, which like ultraviolet or the methane absorption band at 889 nanometers. So here you have some lucky astronomers, Jean-Luc Dauvergne, myself, Christian Villadrich, Thierry Legault, with François Collat, the professional who is nice to give us the access to this telescope. So now I will present you, it will be more, let's say, images. I will present you some results with this 1 meter telescope, all done by amateurs. So it's extremely useful in, as I said, on Jupiter in the methane absorption band at 889 nanometers with a nice resolution from one pole to the other. It's really, it has nothing to do with what we can do with our own telescopes. So, of course, when doing such images, we also image in visible and infrared wavelengths to have a full coverage and to be able to clearly identify the features which are above the cloud level and bright in methane absorption bands and less bright in the others. We also participate with, on Jupiter to the DETECT project, which is a project for trying to detect flashes impacts on Jupiter, on some acquisition movies, and also logging how long are the movies that have been run through the program, so we know for which length we do not have any detection, and when we will get some detection, we will be able to really refine the impact rate at Jupiter. So this is another example of an image, an infrared image. So maybe it's not that striking, but looking at these very small features near the poles, it's really rare to see that on amateur images, regular amateur images with smaller telescopes. So, of course, all of the work which is done at Pic du Midi is shared with the professional database, which is run by IOPW and with the other amateur organizations. another one, invisible wavelengths, where again you see very fine structure in the near the poles. These images were done by Jean-Luc Dauvergne. Saturn. We also observe Saturn. So this is an image that I took 1 year ago at Pic du Midi, where we see the hexagon, which is nicely resolved here. And it was 2.5 years after the first eruption of the Great White Spot, so we could also identify, it might be difficult here, but we can identify some traces here in the latitude range where the Great White Spot was spread. Another one I took, and which was processed by Emil Kreikamp, it's very interesting because we see very nice details in the rings here with the Encke division, and we can see also I think the Maxwell minima inside the C ring, and we can see some traces of a Great White Spot here. Next, the outer planets. Uranus is extremely interesting to image at Pic du Midi. In 2011, Jean-Luc Dauvergne imaged for the first time a spot on Uranus. So we can see it here. Maybe it's not that obvious. It's also here at different time frame over several months. And of course, it was interesting for the professional who also use some higher diameter telescopes in their study of this eruption in 2011, and it led to a paper in Icarus by Sromowski and colleagues. This one was made by myself 2 years ago. So there is an interesting detection, no spots, but interesting detection of the belts of Uranus here on the North Pole and the equatorial belt here, which were resolved with a 685 nanometer long pass infrared filter. And this had a very special effect. By publishing that to the forums and to other amateurs, I've seen amateurs regaining interest into Uranus and trying to and taking the challenge to image also belts on Uranus. And I could advise them to use the same kind of filter, but with a bit of red in order to be more bright. And they actually succeeded, and now, even this year, we might have had the first image of a spot by an amateur with an amateur equipment on Uranus. And last, Neptune, even farther, smaller. Of course, it's not as detailed as Uranus. But here you can see that in last year I could image a bright spot. And other amateurs with 14 inches diameters could also image this spot, and I made a small study on that, and I present a poster. I will present a poster afterwards regarding these observations. And of course, it also interested professionals who used professional equipment to identify this spot. So, as a conclusion, amateur observations at this telescope is a nice example of pro-am collaboration in planetary observations. It's one step ahead using our own equipment. It's using an equipment, a professional equipment. It brings results in planetary science, and because we provide this data to a professional, and there are some results. It's also, as I have said, for Uranus, it drives on the other side the amateurs with their own equipment to take over challenges by seeing a fellow amateur astronomer doing things on this 1 meter telescope. And of course, it's a very nice, an excellent opportunity and a very nice gift for an amateur to be able to go to a professional telescope and observe on a professional telescope like at Pic du Midi. So that's it for my presentation. Do you have any question?
Do you see the Uranian rings, and what is the exposure time for
which rings?
Uranus?
Sorry.
Uranus rings.
Last year with Andor Neo camera, Jean-Luc Dauvergne could detect the rings, but that was not really a clear picture. And I do not remember the exposure time that he has used, but it was in, I think it was in methane bands, in order to have it, of course, brighter than the planet and not being affected by the brightness of the planet in other wavelengths. I don't know. Honestly, it's, I think it's hundredth of a millisecond for the exposure time.
Thank you.
This might sound like a very silly question, but I am training to be an astronomer. I'm a PhD student. But one thing I really enjoy doing is taking astrophotography of the, and I want to start doing it of the Jovian planets. And well, not like, not the close-up ones, but the tracks of them. Is there any particular sort of website or book you can recommend to start learning how to do this kind of photography or observations?
For observing planets?
Yeah.
Actually, we are writing one in French.
Well, there we go.
Which we intend to also publish in English.
Right.
So I will advise that one. For English version of such books, I do not know. Maybe Richard. Richard, you know some of his books?
It's actually a good question. It's not really been put down in detail. Each person, to some extent, keeps it to themselves.
Because I'm not gonna lie, I started doing astrophotography when I went on my first observing run last year, and I've done some star trails and things, but I want to be able to take good, like, individual images of the sky, like you see a lot of really good amateur photographers, amateur astronomers taking beautiful photos.
There is one very famous amateur astronomer who is Damien Pitch. He has not written a book. Maybe he has written a chapter in one book about astrophotography in English, and he has also issued a DVD for showcasing how to use the software for processing the acquisition videos. Last question, maybe.
To comment in an answer to the last question, if you're looking for wide field astrophotography and you're talking about star trails and so on, go to the website twanight.org. It's the world at night, and there are tutorials there about how to do it. These are the guys that produce some incredible time lapses and single images, including tracks of retrograde loops of Mars and various things there. So they have a lot of information. The world at night. Yeah, and the director of it was sitting next to me a few minutes ago and just went to another one here, but we can find him to talk to. He'd be the best source.
Okay, thank you. So now I will hand over to Alexandre Santerne, who will talk about what amateur can do also not only on the solar system, but also in exoplanetary science. Thank you.
Yeah, thank you, Mark. And also thank you for you to have organized this session since several years already. So yeah, congratulations. So let's move a little bit further than the solar system to planets that actually we don't resolve, or we start resolving them by ground-based telescope, but we are looking about planets around other stars than the Earth. And I was trying to make kind of a small review about what we amateurs can do and what professionals can do as well with amateurs in this very hot topic. That just actually started almost 20 years ago. So just the outline of my talk, I will just come back with the big pictures of why exoplanets, and then I will come back briefly about photometric collaboration with amateurs, and then I will spend a lot more time, because it's quite new, about spectroscopic observation by amateurs that are actually and will be helpful for professional exoplanetology. And then my conclusion and perspective. So first, the big picture, what do we want to, and why are we looking for exoplanets? First, because we don't know that much about planets. You know probably a lot of things about giant planets from the solar system, but there are just 4 giants and 4 rockies, and only one system, which is very difficult to make good statistics with just one system. So if we want to learn about their formation, their migration, how they evolved, to want to know about their, for example, the formation rate, about what kind of stars they form more, what the diversity of that planet, the different population, you need, of course, more than what we have in the solar system. And especially there is a last question for future, what about the condition for habitability. So for that, we have kind of really good planets that we can get from other systems, which are the transiting one. It's planets that actually pass in front of their star. So it's a very aligned system where you can see the planet going in front of the star. And during this event called transit, we can detect the drop of flux, something like the occultation of the Galileo satellites. But there it's planets and stars. And so if you get the radius, if you get the photometry of those stars, with the planet passing in front, you can get the radius, if you know the radius of the star, of course. And then we can also use some spectroscopic technique like radial velocities to measure the mass of the object. And if you have both, the radius and the mass, you can constrain the bulk density of the planet, and from that you can constrain somehow the structure of those planets. Of course, the precision that we reach is uncomparable with what we have with a solar system object. But we are trying to improve our techniques and to get the best precision ever in order to constrain even better the models. And if we know the mass and the density, you know the nature of those planets. For example, if they are rocky, if they are some ice giant planet, or if they are giant planets like Jupiter or Saturn. And actually, we found that there is a continuity in density and in mass and in radius about this planet, from the Earth to the mass of the Earth to the mass of several tens of Jupiter masses. So it's really impressive. So what can amateur do on these fields? And first, in photometry, there is actually just one slide, because actually amateurs are doing a transit of exoplanets since almost more than 10 years already. And they are really impressive in precision in photometry. It's really impressive. So one of the main niche actually for amateurs is to keep updating the ephemeris, because, for example, when we will have the James Webb Space Telescope on fly, if it fly one day, and if it can open fully as well, we will be very interested to observe the atmospheres of those planets, and for that we will need to know when the transit occurs. And if we have some transiting planet that we don't observe them for years, we might lose the ephemeris of those planets, and it will be really a mess to ask for James and to get James Webb Space Telescope time, and not to know when the transit will occur. So we need to detect and to keep in the updated ephemeris. Then we can search for other companions in the system by transit timing variation, which is a technique that needs to measure very accurately the time of the transit. And if you have, for example, an external or internal companion that is not transiting, it might perturb gravitationally the transiting planet, and this can make some variation like this in the time of the transit against the time against the periods. And for example, here you have a nice example of a 1 Kepler object system, probably because you have here the residual of the linear ephemeris from this planet, and you clearly see that it's not linear at all. And so there is another companion, but after 4 years of almost continuously Kepler data, we are not able to say if this variation is the green line there or the red line there. And you have a network of amateurs and professionals in Germany, led by Germany. It's the KYNet network. Here you have the link there, and they try to continue the follow-up of a transiting object from Kepler, just to know if to fully constrain those transiting system and to detect other planets in the system. Then we can also study stellar activity with planet spot crossing event, like when the planet crosses a spot. And for example, here you have a transit. I don't know if you see it well, but it's an amateur observation of a transit of a planet in front of a star, which has a huge spot there. And when the planet crosses the spot, you have a jump in flux, which is there. And if you see this transit, if you observe all the transit, you will see the bump, this little bump going and moving inside the transit, which helps us actually to as well understand better stellar activities. And you can also detect transit. This is another niche for amateurs to try to detect transits on planets that are detected by radial velocity surveys. They have a very low chance of transiting, but if we don't try, we won't find any. And actually, it's also one program that we have with some amateurs in Europe to try to detect planets discovered by spectrographs. So now move on to spectroscopy, because there is a new niche from amateurs or advanced amateurs, like Mark was telling you just before. And so it's amateurs radial velocities. It's really a difficult, challenging technique, but now it's at the level of amateurs or advanced amateurs. Here is just an example of a spectrograph. It's an HL spectrograph with a resolution of 10,000 from the Choliac instrument. And so you have the spectrograph inside. It's linked with the fiber. You have the camera there. You have also the HL spectrum there. They make some calibration. Okay, there is a small recipient there with a cross-correction function. And at the end, they were able to detect the planets clearly. This one is Tobutis, is one of the easiest, brightest planets. So it's pretty easy, but it was detected in 2002 and confirmed by amateurs almost 10 years after. And actually, they did not observe only one, they observed 4, including there, you have 51 Pegasus, the one from 1995. But it's, okay, barely detected. And actually, the guy that did the detection, they built a new spectrograph with the higher resolution. Now we are speaking about the resolution of 50,000. So it's not, with an HL spectrograph, so here you have the grating, the collimator, the camera is there, you have the fiber getting into the spectrograph from here, which is linked with this, right there, small telescope. Here you have the astronomer. And with this new spectrograph, they were able, okay, this is the raw images, they were able to detect 51 peg, almost as well as LOD in 1995. With this detection might be in future the result from the Nobel Prize. And almost 20 years after it was done with a 10 or 20 centimeter telescope, which is really amazing. So just to plot you, because I found it very, very nice, it's kind of the more lure, but not for CPUs, but for spectrograph. And this plot represents the radial velocity accuracy against the year of commissioning. So when I was actually not born, there was Coravell. And then LOD, Coralie, etc. And we are going down with the espresso, and it's following kind of linear law with time, or not linear, but linear in log. And actually, if we plot exactly the same slope with amateur spectrograph, we have this really nice slope, and I don't know where actually they will stop. That's really interesting. So in 4 years, they might reach actually below 10 meters per second precision. That's actually a challenge that I told them. Okay, so there are 2 niches for radial velocities amateurs observation. The first one would be to observe massive planets or brown dwarf, because actually we don't know that much of massive planet and brown dwarf, and the border between those two is very interesting, because actually we don't know exactly what the brown dwarf is, or what the mass limit between brown dwarf and planet. This is really a huge debate since more than 10 years. And one of the options would be to go to observe bright, fast-rotating F stars, because those were not well observed by radial velocity surveys, because they are not the best target to find small planets, because they are rotating fast, because they are hot, they are massive. So it's definitely not the best target to find rocky planets. So we kind of remove them, but by removing them, we might miss some massive companion. And actually, transit surveys like Kepler and Corot found several brown dwarf and massive planets around those fast rotating F stars. So it might be something to be done. Actually, I'm not really encouraging the amateurs to do this, because it's really time consuming, and we don't know in advance if there are planets there. So they might really load their time, maybe just for nothing. So I was telling them recently, and I will try to convince them in future to work more on the characterization of giant planets from transiting surveys. And we will have, okay, that is today. That is the Kepler candidates. You probably have heard about Kepler. And this is all the dot there. It's the estimated radial velocities amplitude to detect, to characterize their mass as function of the magnitude of the star. And as you can see here, the magnitude of the star, of the hot star, is pretty faint. It's from 12, the bright end, to 16 for the faintest end. And this is definitely not worth for amateurs. Even for spectroscope, from professional spectrograph, the two lines there, the red one is the photon noise reached by HARPT on the 3.6 meter telescope in 1 hour exposure time. So even with professional telescope at ESO, we have some trouble to get the mass of all of them. So it's definitely not worth for amateurs. But we will have a bright future. We will have space missions with the S at the end that will focus on bright stars. We have actually K2, which is the second life of Kepler, which observes the ecliptic plane, that will focus some part of its observation on bright stars. In bright, I mean brighter than 12. And we will have 2 European missions, Cheops and Plato, that will observe stars as bright as magnitude, let's say 6, 7, maybe below. And TESS as well, that will observe all stars in the sky brighter than 12. So those stars are definitely much better for amateurs, and they can really contribute to this follow-up and to this science project. So once again, this is the expected yield of exoplanets from TESS. So with the comparison with Kepler, so the Kepler is all the blue dot there. You have the magnitude here and the radius of the planet there. And basically, well, all the Kepler stars are very faint. All the TESS one will be bright. And this range there, it will be some object that have a large radius or large mass, so we can probably detect them from the ground and from amateur spectrograph, and they are bright. And those will definitely not be the first priority target for Espresso or ARPS or professional telescope, because we will look at those ones which are the brightest and the smallest planets. So there is definitely a niche for amateurs to go there. No, not to go physically there, but to follow some target there and to find themselves and characterize the planet. And then we have Plato, of course, from ESA, that basically the same picture. It's not a full sky, but it's 42% of the sky, almost the same. We are going down to magnitude 4. And this is, once again, the expected planet yield against VIG magnitude. All the blue dots there are Kepler, and Plato will be there. This is range, this axis is relative to the habitable zone. It's not really matters, but all those candidates that we will find with Plato will be bright. And this is definitely something that amateurs can do. And for example, if you have a comparison, for the 3 main space missions, and Plato, Kepler, and Coro, the number of bright stars that have been and will be observed, I mean, in bright, better than magnitude 11. With Coro, we observed something like less than 400. With Kepler, it was almost 6,000. And with Plato, it will be more, or about 85,000 stars brighter than magnitude 11. So a huge amount of stars that can be done with amateurs. So my conclusion, exoplanet studies are accessible to amateurs, not only in photometry, but also in spectroscopy, and this is really recent, and I really push the amateurs to buy spectrograph, to practice, to be ready for 2017, where TESS will be in the sky, and of course 2014, when Plato will be there as well. So the study of giant exoplanet transiting bright star could be performed by amateurs, and there are still a lot of science to do with giant planets, even if most of my colleagues are still focusing now on rocky planets, and they just forget about giant, and there is still some science to do. So in photometry, for Plato, there is something as well that can be done to check for background eclipsing binary that just diluted and pollute the signal that we found with Plato and TESS. And in spectroscopy, there is definitely something to be done in radial velocities, at least to screen out false positive like eclipsing binaries or things like that, or to characterize giant planets. And there is a room for a large professional amateur collaboration in the next future space mission, as I already told you. And I hope I convinced you. And just before finishing, because I think I have just still a couple of minutes, I just want to tell you that this collaboration, at least in France, was possible thanks to what we call the ProAM school in France. It was first started in 2003 in Oléron, and then there was Folium done in La Rochelle, and the next one will be next year. We don't know yet exactly, but maybe it will be close to Geneva. This is the group picture, and the recipes to have new collaboration, because actually this collaboration with amateurs in France started in La Rochelle in 2009. So I will give you the recipes for the nice cocktail, which is just to put in the same room, the same building, the same residence, almost half of pros, half of amateurs, check it for 1 week, and then you have new collaboration. And some key dates in 2006, there was, because some people, some amateurs starting spectroscopy, meet some professional that were interested by spectroscopy amateurs. They meet each other, they discuss during 1 week, and they start a really interesting and really producing professional amateur collaboration spectroscopy. And in 2009, improved in 2012 then, we start a collaboration with amateurs about exoplanets. So now I'm just asking a question, what about an European program meeting? Thank you.
Okay, thank you, Alexandre. Do you have any question for Alexandre regarding ProAM collaboration with Exoplanet?
Well, I'm convinced that such a European ProAM meeting could be part of the Europlanet research infrastructure project if selected. I mean, this is one typical kind of meeting that should be really supported by Europlanet. So let's wish Europlanet project would be funded, and yeah.
And
there is this project that's busy, which is planned to distribute planetary observation from amateur to the professional. So,
yeah, but the idea, sorry, the idea behind is not to have it only about planets. It's to have it about all fields in astronomy. Of course, I think we have to focus those in thematics, otherwise it will be just too wide. So my first idea was to say, okay, maybe we can do 1 year about planets, the second year about pulsating stars, the third year about binaries, and then go back to planets or something like that. And try to find some funds to organize it.
Maybe Pedro Russo from Leiden University. One thing that we organized in 2010 and 2011 was a common meeting between professional and amateurs during the European Week of Astronomy and Space Sciences. So we had a session that we organized at that meeting. And I think another possibility that we've already been talking is even creating maybe a working group within the International Astronomical Union to look at these matters and trying to see what can we do to improve the relations between the two. And I think that could be a good forum to start a discussion, not only planetary science, but also with the other astronomy-related sciences.
Yeah.
So we should talk afterwards during coffee break.
Okay. Do you have another question? No? Okay, so as I mentioned at the beginning, the last talk was cancelled, so we are just fine in time. Before leaving, I just want to mention that after the break, we will have the session regarding citizen science and the link with professional and amateur astronomy. So it's kind of complementary to this session. And just one thing regarding the poster of the session that will be presented later on. Let me just open it. We have also 3 posters. So the first poster is from Olivier Moussi, which is regarding ProAM collaboration in planetary science, which is based basically on a paper which has been published and co-signed with, I think, 60 people. Half of them probably professional and half of them amateur, so it was a really interesting work and summary of the kind of ProAM collaboration that we can do in planetary science, in all planetary science. The second poster is more focusing on the country, of one country, on Finland, where there is a program network which has been built for coordinating some private amateur observatories and providing the link to the professional community. And the last one is one from myself regarding the bright spot on Neptune that I already talked about. So it will be after the session at 5:45 that this poster will be presented. So thank you to all of you for your participation to this session, and see you maybe in the next session. Thank you. Let me just take this. So I will just make sure that I will have that on my key, and I will. And okay.
If any of the speakers from the next session are here, can you please upload your presentations? I don't know who's here. Hello. Yes. Okay. I'd like to talk. Oh, thank you. I would like to know anything I can help. Oh, okay. In fact, I'm not sure. Are you there's a person at the headquarters who knows Kevin from OAD? Kevin, yes. Yes. So are you part of the same? No, you're separate. Okay. We're a different office, but we assist the office. Okay. Mark, excuse me, I'm just trying to, but no, definitely, I'd love to talk to you on this. Okay, so you know what, I don't know who's doing it, but you are my next speaker. Okay, you know what, I guess I need more, can you switch yours and just put it in this directory, I guess. Yeah. Because I'm not a PC person, but let's try it anyway. Scan. scan the drive. And I have to go find 2 talks that are going to be done by Skype, so that's why I'm kind of running right now. If you don't mind, are you going to be here till after?